Great pleasure to give a talk with your organization. My name is Amine Bermak. I'm with the College of Science and Engineering at Hamad Bin Khalifa University. So first of all, I would like to start with what I call the perfect storm. There is an unprecedented processing power, storage capacity, and also access to knowledge, and most importantly, big data and AI. We can see nowadays a digital revolution which is disrupting almost every industry in every country, leading to transformation of the entire system of production, management, and governance. And there are many technologies that have emerged that are leading the way for this development. This includes robotic, Internet of Things, autonomous vehicle, 3D printing, nanotechnology, biotechnology, material science, energy storage, quantum computing, to name a few. And as you can witness from this slide, basically the growth for IoT, Internet of Things, is going at an exponential pace, and it's actually exceeding Moore's law. And we can see that by 2021, this year, we're expecting to have 300 billion devices that are connected to the internet. This is what we call IoT. So we're not talking about only smart mobile phones, but sensors that can connect to the internet and seamlessly communicate with the network. And also these devices will interact with the environment. So they are equipped with sensors and processing. So in this area of IoT, wireless sensing platforms are very important. And basically we're talking about, that's why I call it autonomous integrated smart sensing systems that are capable of sensing, processing data, and also smartly communicating with their peers in the network. So basically this will enable smart cities in the future. The three pillars that I can think of in order to design IoT devices are related to first sensors, and then processing. You need to be able to process the data and also communicate the data, because communication is also becoming very important. In the sensor area, there are many challenges that need to be addressed, because all of these devices, when we talk about IoT, cost is very important. And also autonomous operation is important, because you don't want to go and calibrate the sensor. You don't want to go and change the battery. And therefore, basically, hello? Can you hear me? Can you hear me? So basically, there are three pillars: sensors, processing, and also communication. In the sensor area, we need to have sensors that are self-calibrated. They can calibrate themselves. They can process the data, and they can communicate with the network. So we talk about self-powered sensors, which is a very important area. We also talk about energy harvesting and also intelligent data converter, because in most of these applications, you cannot transmit all of the data. You need to transmit only information rather than data. All right, so my agenda for this talk today will be to look at two case studies. We will look at electronic nose as an IoT device, and we'll be looking at vision sensor also as IoT device, and I call it passive wireless camera network. And in both of these areas, we will look at how to address low power operation, how to reduce the power by reducing the requirements for the ADC, and also how to achieve self-powered, even in the case of vision sensors. So I would like to start with the eNose application. So electronic nose have been emerging in many applications like automobile safety, air quality, food control, and also medical, because we have many applications in the medical area where actually you can detect, for example, bacteria by looking at the smell of the bacteria. So basically, even healthcare is becoming an application for electronic nose. So one of the objectives that we want to achieve is to implement this as an IoT node, which means it has to be very low cost, and it has to be integrating all the functionality for eNose, even the classification part, which is important because you are receiving multiple smells and multiple gases, and you would like to classify them. So the idea is to have a gas sensor array. You acquire the data from the sensors, and then you try to encode this data and further try to classify and recognize this data. All of this needs to be integrated in a very compact, portable electronic noise microsystem that consumes very little power. It has to be low cost and also robust. This is actually, this image that you see on the bottom right is an example of a system that we implemented. It's a fully integrated electronic nose that includes even the training algorithm and also the classification. So let me go through one of the applications that we have implemented in my group. So we implemented the tin oxide-based gas sensor, where we have an array of basically gas sensors that are a MEMS structure. So a suspended MEMS structure that includes a sensing film at the bottom, and also polysilicon in order to heat the film. And this basically sensing film was coated with different sensing material and also with different post-treatment in order to obtain some kind of a fingerprint. So the idea is not to not just detect one gas, but also to detect different gases and let it operate as an electronic nose. So this we built an array of 4x4, and as you can see, for each sensing layer within the array, we used different sensing material and also different doping in order to tune the sensor with different parameters. So if you look at the basically the mathematical modeling of tin oxide sensors, they are actually quite well known. This is actually very old paper, 2008. People try to model the tin oxide sensors, and it turns out that they can be modeled as power law approximation, which means that the output of the sensor, typically it's a resistance that we look at, will depend on many parameters, and these parameters also depend on the concentration of the gases and also the gases. So Cj represent the gas concentration, Xj is actually the sensitivity, the output, and then alpha and gamma are parameters that depend on the concentration of the gases, but also on the gas itself. So the gases and their concentration, and also they are dependent on the sensing material that you use. So every sensor within the array will have a different alpha and gamma. So in order to extract these parameters, alpha and gamma, it requires very accurate measurement and knowledge of the gas concentration. You need to know the gases, but also their concentration, because in the equation you have both parameters. And this turns out to be a very difficult task. So the idea that we come up with is actually a novel, basically pattern or extraction technique, where the idea is actually not to look at only one sensor, but to look at the log response of the sensor. So if you do the log response, then the concentration becomes additive because the log of this product becomes additive. And we can actually, we propose to use another sensor, let's say sensor 1, as a reference. So we have basically, instead of reading the output from each sensor, we try to read it with respect to a given reference within the array. And instead of reading the absolute value, if you read the difference of the log, then you're going to cancel the concentration effect. And you end up with parameters that are concentration independent. So by doing this log and then having the response with respect to a difference with respect to another reference node or a reference sensor, then accurate measurement of the gas concentration is therefore eliminated. So based on this idea, we created a signature matching type of recognition or classification, where we start with the sensor array, and then in presence of gases, then we try to generate spikes, and these spikes are actually proportional to the log, and then we try to look at the timing of the spike, and we subtract the timing with respect to a reference, and therefore we obtain this basically log difference. So basically for each node that you saw in the array, we try to generate a spike that is proportional to the log, and then we try to look at the spike pattern, but because it's a spike pattern, then the difference will be independent to the concentration. And the whole idea is actually to classify these gases based on recognizing the spike pattern that we have. I will try to explain later how we can obtain this in hardware. So basically our bio-inspired encoding scheme will be summarized in this slide, where you have an array of sensors, and these sensors are associated with a bit of computing. It's actually very simplified computing, which compute the log and also generate a spike. So for each node within the array, you will end up with a spike. And therefore, you try to, when you have an unknown gas that will come in, basically you have your array that will fire at a given sequence, and you get a given sequence for a given gas. The very interesting thing about this is, if you use this differential readout, it means that if you have different concentrations, what's going to happen is, because your enter spike, or the difference between two spikes, is proportional to the difference of the log. And because it's proportional to the difference of the log, it becomes independent of concentration. So the enter spike timing is actually independent on concentration. So if you have a given gas and you vary the concentration, then you get exactly the same spike pattern, except that this spike pattern is shifted. So by looking at the shift, you can actually deduce the concentration. And by looking at the spike pattern, you can detect the gas, which is actually a very interesting, let's say, pattern recognition algorithm. So how can we implement this in hardware? It turns out that the implementation is actually very, very simple. The idea is the tin oxide sensor gives you a variation of resistance. Then if I can translate this variation of resistance into a log, and then I generate a spike, then I look at the rank order and I can classify the gases. In fact, by looking at the delay or the time to first spike, you can even deduce the concentration of the gas. So how can we do, for example, this conversion from resistance to the log, and how can we generate the spike pattern? So actually you can do that very easily by having a current source that will inject a current into this array of resistance, and you can control it. So you have the array of 16 4x4 resistances, and you can drive a current into the resistance. And then you can also basically discharge this voltage that you have here into a capacitor. And then you compare this into to a certain reference, and you generate a spike. Okay, so basically this is based on a very simple model where we try to first charge this node through this current source. So we get V is equal to Ri, and then we discharge this voltage through a capacitor. And we know that discharging the capacitor through basically this scheme will give us an exponential discharge. So basically the voltage at the output will be proportional to the exponential of the time to reach a certain threshold. If you look at the time will be actually the log of the voltage, because basically voltage is equal to the exponential of the time. If I do the log of the voltage, it's going to be proportional to the time. So this time that you see, in order to reach a certain threshold, will be a log function of the voltage. What is my voltage? The voltage is I times R, and the R is actually the resistance of the sensor, and therefore I'm getting the log of the resistance. And this is exactly what you want, because you want to have the log of the response and convert it into a spike. This circuit, just an RC circuit, will do all of this functionality. If you add a comparator at the output, then you get the spike. So this means that we can obtain all of this functionality without even needing an ADC, an analog to digital converter. And therefore, I can actually reduce the power consumption of my array. And in addition to that, it's ADC free. And in addition to that, the output is digital. So you can process the output, the spike pattern in digital way. You don't need any analog processing. So it's ADC free as well. So based on this idea, actually, we built a platform. And this platform includes the sensor and also this log and basically comparator. And then we added a Bluetooth chip in order to communicate, let's say, with a laptop and to communicate with the outside world. This has been fully characterized and tested. So it's a very basic, simple platform. And the good thing about this is a new gas will give you a new pattern, a spike pattern. And basically, every spike pattern will correspond to a given gas. And therefore, you can classify gases. If you have a new gas, you just need to store basically that pattern in a memory, and then you can recognize any gas. So it's a flexibly scalable architecture, and it can also recognize all the gases that are programmed inside the memory, because we have just a lookup table to store the pattern. And also we can deduce the concentration by looking at the time to first spike, which is the delay of getting your first spike. So this is actually a platform that we have in my lab. So we have an air pump where we can inject gases. You can see the platform is inside the gas chamber. we inject the gases, and this will communicate to the laptop, and it will give you the spike and also recognize the gases. So it's a very simple pattern recognition algorithm, and it's also a whole system that recognizes gases and also recognize different smells. Now I would like to move to, so this is realized like an example of IoT. I have an IoT device that can recognize, that can process data, and also communicate wirelessly. A second case study that I want to share with you is actually, can we turn cameras into IoT devices? There are many emerging applications for wireless camera network, and the idea is to have these cameras as IoT nodes in order to be deployed for large-scale applications. So, for example, environmental monitoring, environmental surveillance, medical assistance of elderly people in homes, wildlife monitoring, traffic and vehicle control, military applications, structural health monitoring. All of these applications, they require cameras, but the idea, because you need many of these cameras, we want to deploy them at a large scale. So we want to obtain wireless camera network, and the idea is also to have these cameras operating just like a normal, let's say, temperature sensor or a simple sensor. Well, of course, there are four main challenges in this, and this is what I call install and forget electronics. So I want to install this camera and forget about it. I don't want to go and change the battery. I want this camera to harvest the energy from the environment and self-operate itself. So in this very harsh requirement, of course, low cost is going to be important. You need to design this at low cost because you want to deploy this camera at very large scale. You want to also to preferably have what we call self-powered, which means you don't need to have a battery. You harvest the energy from the environment. No human intervention for maintenance. You don't want to calibrate the sensor because otherwise it will become expensive. And last but not least is actually, because communication here is very expensive when you communicate, especially in vision, and therefore it will be interesting to have information-based camera rather than data-based camera. What I mean by that is, let's say your camera is installed for wildlife monitoring. You don't want to turn on the power unless there is something that you are interested in and you would like to capture. So for example, you detect motion, you detect certain features in the scene, and there you switch on your camera, because otherwise communication will kill you and you need very power hungry, basically battery and power hungry circuitry. Basically, we try to do that in my group, and the idea that we were exploring is actually how we can basically design, address these challenges where we need to transmit a lot of data, and also vision sensors are very power hungry. So the key question is, can we use light to self-power the sensor? And this is what we have been interested in my group. And also, can we transmit information rather than data? And the objective is to design very low power vision sensor to make them self-powered, and also to design intelligent data converter. Instead of having a normal analog to digital converter, we would like to have an analog to information converter rather than ADC. So let me share with you some of the work that we have done in this area. So instead of using a conventional image sensor, where the idea in a conventional image sensor, which is based on a 3T structure, a 3-transistor structure, you have a photodiode. You reset the photodiode. When you reset the photodiode, then the voltage on the photodiode would be set to VDD. Then after that, you disconnect the reset, and you try to keep the photodiode floating. When the photodiode is floating, when the light comes into the photodiode, you create a reverse current. This reverse current will discharge this voltage that was initially at VDD. So you have a discharge voltage, and after a certain integration time, you sample the signal and you try to read delta V. So this is a conventional imager. This is the concept being used for your iPhone camera and other cameras. So you reset the voltage to a certain, and then voltage V supply. You monitor the photodiode voltage, and after a certain time, you try to measure this final photodiode voltage. And you repeat the process for different frames. So what are the challenges with this? Because you are measuring a voltage and you reset a certain VDD, your dynamic range will be limited by the supply. So you cannot exceed basically the supply voltage. And therefore, you will have a lot of pixels that will saturate, which means they discharge quickly and they reach zero and therefore they cannot capture more light. And this is what we call saturation. So especially if you have integration time that is long, if you integrate for a long time these charges, then a lot of pixels will saturate. And that's why usually when you have a camera and you try to capture a scene inside a dark office, you have the light coming from the window. All of these pixels in the window are saturated and you see them all white. This is because all the pixels in that area have saturated, and therefore you cannot distinguish between the pixels and you cannot have contrast in this area because you saturated. So this is explaining the concept here. If I choose the integration time to be very short, then I don't saturate, but I don't get a good signal to noise ratio, especially for low illumination. If you choose a high integration time, then you have a good signal, but the problem is for highly illuminated pixels, you saturate, and you cannot distinguish between bright areas in that window example that I gave you. So aggressive reduction of voltage swing with new technologies, with new CMOS technology, we know that we are dropping the supply. And this will make this problem even worse because the swing that you are playing with is limited to start with. So very high requirement also in terms of computational requirements, especially if you want to transmit the video at 30 frames per second. And this is all very challenging requirement for basically hardware implementation. Now, the question that we ask ourselves in my group is, can we learn from biology? How is the biological vision done? And if you look at, basically, this is actually a slide done by Toby Delbruck, I think it was in the 80s. He tried to record the signal from the retina of a turtle. Turns out that our visual biological system has some kind of adaptation mechanism, which means that basically you have a certain response to light that will give you the response in the retina. And it looks like this response is adaptable. It adapts to the dynamic range. So if your illumination is low, then your slope will be like let's say to the left. If your intensity, the light is stronger, then basically our biological retinal system will adjust the response to the right. So this means that sensitivity is always excellent. Okay, you have very good sensitivity because you have a good slope, but also at the same time you cover a wide dynamic because you are shifting this response from left to right. So it's a gain adjustment mechanism that is biological. And also information are encoded not in the voltage domain, but in the time domain. So when you look at the transmission between, let's say, the visual cortex and let's say your retina, you notice that there are spikes, which means basically the amplitude does not matter, but the timing of that spike is important. So we thought, is that a possibility to get some inspiration from this concept? And the idea actually, it's possible to get some inspiration from this. And this is what we call time-based vision sensor. Instead of looking at the voltage, we turn the concept into time domain. So we have a photodiode. Instead of resetting and waiting for a fixed time to get a certain voltage, the idea is to fix time, not to fix time, but to fix the voltage. And then basically when you have different integration time, when you have different integration slopes, because the voltage is fixed, you're gonna fire at different instants and you have timing encoding rather than voltage encoding. And this will give you dynamic range, basically immunity, because you don't depend on the voltage. Now you're just reading time. So basically the concept is very simple. We start with reset, and then after that we just monitor the output because we fix the voltage. And whenever we reach the voltage, we generate a spike, and this spike will give us a timing information. So based on this concept, we built a sensor. We call it a PWM sensor because actually we are modulating the pulse width, and it's actually PWM sensor. So the idea is actually to reset the photodiode, then you monitor that voltage. If you have a very dark pixel, it's going to take more time to fire, and therefore you get a time instant that is here. If you have a very bright pixel, it's going to fire earlier, and it's going to give you this timing. And we built, I don't want to go into the details of this because it's going to take me a lot of time, but if you are interested, I can send you some papers, and it works beautifully. And I'll actually, we designed a camera based on this. This is a camera, and actually this is the images that we obtain from the camera. And as you can see, we can obtain more than close to 100 dB dynamic range as compared to only 60 dB in a normal imager. So it turns out that using this time concept is actually also very interesting for many applications. because you consume power when you fire, because you're monitoring the voltage with a certain constant voltage. When you reach the threshold voltage, you fire, and therefore you consume power. So if you look at the power over time, it's actually just the histogram of the image. Because if you have a lot of pixels that fire at a certain instant, you consume a lot of power. And this gives you a lot of pixels that have that particular code. And it turns out that if you plot just the power consumption over time, that's the histogram of the image. Also, you can actually use very interesting signal processing techniques in order to improve the quality of the image. For example, instead of using a uniform quantizer, I can actually look at the firing time when I reach the threshold, and I can see that I have most of my pixels, they are firing here. I can actually tune my quantization level to focus on this area and give me more contrast in my image. So you can improve even the quality of the image, not just the dynamic range. And we have done a lot of processing based on this. I don't want to go into the details of this, but for example, you can do adaptive quantization, you can do basically uniform quantization, adaptive quantization, and different basically schemes that you can implement. More importantly, we discovered a very interesting concept using this time domain. It's actually, you can use it in order to harvest energy and self-power the sensor. Why? Because basically, when you are trying to reach the threshold, your pixel is active. But once you reach the threshold, your pixel is not being used anymore because you got the information and it's free. And it's going to be free for a very long time because basically you can fire in nanosecond and your frame rate can be a fraction of a second. So that's eternity. It means that for a very long time, your pixel is free. So if this pixel is free and it can harvest photocurrent, I can use it in order to inject that current into an energy unit, and hopefully I can self-power my sensor. So based on this idea, we come up with a scheme where we try to monitor the output. Once I get the output, once I reach the threshold, then I release that pixel and I put basically the current into a power bus, and therefore I can self-generate power. This is actually based on a patent that we have, and the scheme has been published and it works beautifully. So the idea is actually at the beginning, you're gonna consume some energy, but after a certain time, because you have more and more pixels that have fired, they are free, they start generating power. So it's like an avalanche effect. Initially, you lose your energy, but then after a certain time, you have more and more pixels that will fire, and they will self-sustain the sensor. So we implemented this. This was actually the very first sensor that was self-powered, and actually we have implemented this prototype, and it was a chip that operates without any external power supply. So to conclude, IoT devices involve sensing, processing, and communication. The main challenges will be, of course, low power, energy harvesting, and actually information-based communication or converter. I didn't go into this because the time is too short. Maybe I can do that another time. And actually, you can see that we have done time domain encoding in both gas sensor and also the vision sensor. This can give you a lot of advantages: immunity against dynamic range, immunity against noise, and also reduced power consumption. Very promising for processing. We can do a lot of very easy digital-based processing based on spike encoding. And we can say that IoT are today a reality for a lot of devices, but still challenging for many areas such as vision and olfaction. And of course, with these hurdles and difficulties, will eventually lead to more opportunities for innovation. And as researchers, this is what we are looking for. With that, I would like to conclude my talk, and I would like to open the floor for any questions you may have. Thank you.